Welcome to this ARC Actuarial Research Centre webinar on the topic of big data and socioeconomic mortality. My name is Andrew Cairns and I'm the principal investigator on a bigger ARC sponsored research programme on mortality and morbidity risk. So the research programme itself is, as I've mentioned, it's sponsored by the Actuarial Research Centre of the Institute and Faculty of Actuaries, which is its network of actuarial researchers around the world. The ARC, it delivers cutting-edge research and covers a variety of research programmes in actuarial science, which will help to equip actuaries for the 21st century. I'm the principal investigator on one of the programs that is sponsored by the ARC, Modelling, Measurement and Management of Longevity and Morbidity Risk. The program as a whole looks at the development of the next generation of stochastic mortality models. It aims to develop a better understanding of the underlying drivers of mortality, and that's in fact the topic of today's webinar. And that's perhaps focused on two things. One of them is looking at base tables for mortality and looking at portfolios of insurance or pensioner lives, and then also looking at trends in mortality over the past and then thinking about what might happen to those in the future. Another of the topics that we're looking at is focusing on what is the best way to manage longevity risk if you decide that you don't want to carry all of that risk within your organization. And then lastly, looking at models and methods for analyzing critical illness insurance and associated morbidity risks. So moving on now to the main webinar itself and focusing more particularly on the underlying drivers of mortality. So I'll give you an outline. So I'll start off with a little bit of background in terms of what we want to do in terms of why we're looking at what we're wanting to look at. I'll then describe the data that we've been using to look at socioeconomic effects in mortality, and that's data for England and for males and females, but at a very highly detailed level in terms of geography within England. I'll then talk for a little bit about the underlying statistical methodology, and then we'll move on for the last part of the talk to look at the results for covering the period 2001 up to 2015. And this will be linking the various predictive variables, so variables that tell us about the socioeconomic characteristics of small neighbourhoods, as well as looking at how much residual spatial variation there is. So in terms of geography, do we have high or low mortality compared to what we might expect? Keep in mind also that this is very much ongoing work, so if you, the viewers, want to ask questions or feedback suggestions, then I'll give you some contact details at the end of the webinar where you can give us your thoughts on this research. So the background for this presentation is that we're focusing on male mortality in terms of what I'll be presenting. However, the results that we get for females, these are extremely similar to the results for males and quite consistent in terms of what predictive variables, socioeconomic predictive variables, matter most, and so we get quite consistent results. Now, so just by way of background, I mean the stylized facts for mortality could be described as saying that mortality varies by socioeconomic group. So what I mean is that we know that wealthier people tend to live longer than poorer people in the population, but there are also lots of other measures of socioeconomic status for individuals and also by different areas. And all of these lead to or predict or will be associated with higher or lower mortality. We also know that mortality varies by region. So, but the sort of classic storyline is that mortality in the north of England tends to be higher than in the south of the England. So is this north-south gap a reality, or is it really down to the underlying socioeconomic mix? So these couple of graphics show for both males and females English mortality, but by deprivation. So deprivation here, it's using the index of multiple deprivation, which is published by the Office for National Statistics. And you don't need to focus so much on the sort of detail of the y-axis in each plot. That's on age standardized mortality rate. But the key thing to take away here is that the most deprived groups, compared to the least deprived, the most deprived groups have much higher mortality than the least deprived. And that's across all ages, although this, of course, is an age standardized plot. So there are these big differences between the 10 groups by index of multiple deprivation. We can also see, of course, that there are improving trends in each of these 10 groups over time, but the gap between the most deprived and the least deprived, that gap is gradually getting wider as the years have gone by, the last 15 or 16 years. And a very similar picture for females, big differences between the most deprived and the least deprived, and a widening gap. Let's now have a look at variation by region. So this map is just showing you the 9 regions of England that I'm going to be looking at in 1 or 2 of the tables, although we will be drilling down into a lot more detail by much smaller geographical areas. And if we look at these 9 regions and look at mortality rates, and here it's for the age group 60 to 69 for males, and the percentages that we have for the 9 regions, these percentages are what do we observe in terms of mortality in a particular region relative to the national mortality rate. So we see here that there is quite a lot of variation between the regions. So the northeast is 118% versus 18%, 87% for the southwest of England. So there is quite a lot of variation here, but I would reiterate that the regional variation that we've seen in this plot, this table, is much less than the amount of variation that we see by income deprivation. So summarising that, we've got variation by socioeconomic group. We've also got mortality in the north being higher than mortality in the south. But we can also say that mortality tends to be higher in the big cities compared with outside of the cities. Now, the key questions here are how much of this can be explained by underlying socioeconomic differences, and how much variation is geographical in terms of what's left over. So after you've factored in all of the socioeconomic variables. And if we see some geographical variation, then this might be due to things such as higher levels of smoking in one area than another part of the country, things of that sort. But things that we can't easily observe in our data sets. Moving on now to talk about the data. So we're looking at England, and the small geographical areas that we're going to be analysing are called lower layer super output areas, which is a bit of a mouthful, so I'll abbreviate that to LSOAs. There are just under 33,000 of these small geographical areas. They are, within each area, they are socio-economically homogeneous, or they try to make them as homogeneous as possible so that similar sorts of people, similar backgrounds live in these areas. So bearing that in mind, that the average size of these areas is on average about 1,600 persons, but that there is quite a lot of variation from perhaps less than 1,000 for some areas up to 3,000 in some other areas. So we have each of these, for each of these LSOAs, we have data for single years, single calendar years from 2001 to 2016, and also for single ages. And by that, what I mean is that we have death counts and we also have exposures. Now, because each of these areas is relatively small, The death counts are the data sets that we have contain a lot of zeros and ones, and so what that means is that we need to take that into account when we're doing our statistical analysis. Now, in addition to the deaths and exposures, we have lots of static predictive variables for each LSOA. So this is predictive variables that are socioeconomic in their nature, plus one or two other variables that I'll talk about. So in terms of these predictive variables, the first group are all components of the index of multiple deprivation, the IMD, but the IMD itself is made up of a number of domains, and the most important domain perhaps is income deprivation, closely followed by employment deprivation. Income deprivation means that it's counting people who are receiving benefits of some sort from the government, whereas the employment deprivation is measuring unemployment in a particular area. We then have other measures of deprivation, so education deprivation, or the number of people with very poor qualifications, crime, barriers to housing and services, so distance to services, and of course, when it comes to mortality, distance to services, although a longer distance might somehow mean that you're more deprived, on the other hand, longer distances might mean that you live in a nice spacious neighbourhood with big gardens and things of that sort, where in fact a longer distance to services might actually indicate lower mortality. Wider barriers is measuring things like overcrowding and homelessness, and then lastly living environment is measuring things like housing quality, are houses unmodernised, and also externally what is the air quality. So all of these are components of the index of multiple deprivation, and we're going to use these in terms of our analysis of mortality. Outside of the deprivation indices, we also have lots of other variables which are often measured by through looking at the census from 2011, but there's also other survey data sets which are done at the level of LSOAs. So we have more detail in terms of educational attainment, from no qualifications all the way through to university qualifications, and by age groups. We have occupation groups, weekly income, average number of bedrooms is one that we will be using in the later results. We then have other data sets which are not so much socioeconomic, but they are important for measuring mortality rates. One of these is the number of people that are in care homes, both with and without nursing, and then the urban-rural classification. And what we've found in our analyses are that whether you're in a big city or whether you're out in the countryside makes a difference in terms of how the predictive variables are linked to mortality rates. So moving on now to the methodology. So just as a reminder, we've got the death counts and the exposures. We then have the national death rates. So effectively for each calendar year and age X, we're adding up all of the deaths and dividing by all of the exposures. That gives us the crude mortality rate for the national level. We're then looking at the LSOAs. So the LSOAs are characterized by a local death rate. So we've added here an index I to represent the LSOA. So that might be above or below the national mortality rate. And then the general model would be that the death count for that particular LSOA will have a Poisson distribution with a mean equal to M times E, the death rate multiplied by the exposures. Although for our purposes, it's the mean of this distribution, the expected value M times E, that is the most important thing, rather than the Poisson distribution. Now, for the general approach, what we're going to do is we're going to look over groups of relatively limited age ranges, so 10 years of age, so for example 60 to 69, and then over also a potentially limited range of years, but it could be 2001 up to 2015, as we'll do later on. I'm going to model this MITX, so that's our key death rate that we want to model. That will be modelled as the national death rate, which will then be scaled up or down by two relative risk factors, F1 and F2, and each of these will be specific to the LSOA, so index I. So the first of these, F1, this is the relative risk due to socioeconomic characteristics, which can be estimated using a variety of techniques, and what I'm going to focus on here is local weighted linear regression. Then we have the second relative risk is F2. So this is after we have accounted for all of the socioeconomic characteristics, what's left. And so F2 is an additional relative risk, which is capturing the spatial effects, and we'll use kernel smoothing to get that one. So continuing, so we've got our single years and single ages. So what we're now going to look at is the classical actuarial actual versus expected. So we count up the actual deaths over this range of ages and range of years here, summing over t and x, summing up over all the observed deaths. We then have the expected deaths. Now, to start off with, we're not going to include any relative risk factors. So in this case, there's no modelled effect. So this is our very basic model. So the expected deaths are simply going to be for each year and each age. The expected deaths will be the exposures for the LSOA multiplied by the national death rate. And we add all of these up over years and ages to get our baseline expected deaths. And then we calculate the actual over expected at the level of the LSOA. So R0I is the actual deaths divided by this basic estimate of the deaths. We now introduce the predictive variables. So we've got a potentially, as I mentioned on the earlier slide, there's quite a wide range of predictive variables. So we probably won't use all of these, but we may use 2 or 3, or maybe 5 or 6 or 7. So we start off with a set of unadjusted predictive variables, but the problem here is that different predictive variables are on different scales. So some of them might lie between 0 and 1, some of them are on a percentage scale, others have already been normalized and can be anything between minus and plus infinity. So because of that, we standardize each predictive variable. So we turn the PIJs into XIJs, which have a standard normal distribution. Now, the purpose of standardization, that's really just to simplify the system of weighting that we're going to use later on in this stage 1. So we end up with a vector, XI, and so that's for each LSOA, we've got this vector of standardized predictive variables. Now, aside from the socioeconomic variables, we've also got urban versus rural. So what we found in our preliminary experiments is that this did make a difference to how well the predictive variables perform. And so we've used 5 different groups. We've got conurbations, which have been split into London and other conurbations, because London has turned out to be different from other big conurbations. Cities, rural towns, and then the really very rural areas. So we're wanting to incorporate this into the whole estimation process. Now I'm going to describe the local linear regression. So this graphic here, this is very much a stylized example. It's not actually the real data, but the purpose of this stylized example is just to give you a flavor of how the method works. So in this case, we have a single predictive variable rather than a vector for each LSOA. Each dot represents the predictive variable for the LSOA, and then the observation that we have, which could be the actual over expected, but it could be something else. Now, in this case, you can see that there's a certain shape to the outcome, the observation, in relation to the predictive variable. So if we were to do something naive, like a standard linear regression, then clearly you could do a linear regression, but you wouldn't get a very good fit. So we want to try to do something different that captures the shape of this quite large data set. So in this style example, so we've got lots of these observations. So there's the predictive variable x, and there's the observation y. Now, what we want to do is to estimate what is the expected value of y, given the predictive variable x. And we do that by weighted least squares. So for each I, so that's indicated in red, so for each LSOA, we're going to calculate this least squares objective function. And within this, we have a set of weights. So instead of the standard linear regression where we have equal weights for all observations, yj, we're having a system of weights which are related to the LSOA that I'm particularly looking at. And the key point is that the weights are high if the observation xj is close to xi, but as xj gets further from xi, the weights gradually decay down to 0. And so when we do the minimization and fitting a straight line, we're really fitting a straight line through points that are near to xi. So we then do the minimization, and then this gives us estimates ai hat and bi hat. And so we repeat this for each LSOA. So I equals 1 up to 33,000 as it would be in our case. So that's 33,000 least squares procedures. And then all we're interested in, we're not really interested in the line itself, but we're interested in simply the point estimate yi hat. Now, we could, of course, also use other methods such as B-splines and P-splines. However, while that works well for one dimension, we're maybe looking at 5, 6, 7 dimensions, and P-splines don't work, or they're quite cumbersome for that sort of setting. So going back to our stylized example, we've got here, I've now got the grey dots, which are the original data set, and now the black dots, and the size of the black dots represents the weights. So the large dots mean that we have a high weight given to that particular LSOA, and a small dot gradually getting smaller and smaller. They mean much less weight. And so we now do our linear regression through these points, with taking account of the weights. And as I say, we don't really want to think about the line, but what we do want is the big red dot, which is the point estimate for the expected value of the observation y. And then we repeat that for each of the LSOAs. So here the red dots are our estimates for each of the LSOAs. And what you can see is that if you connect up the red dots, then it really very much captures the shape of the underlying data set in a way that our linear regression would not. So moving on now to the real data set that we're looking at. So for each LSOA, we are going to estimate the socioeconomic relative risk F1 of I, and we do that by doing this local linear regression. So here's our regression function. So there's for each I, there's an intercept and a slope. We've got NP predictive variables plus the urban-rural classification, and these are all handled in the weights. So what we're trying to do is to minimize the objective function S over A and the vector B. And again, the function here, although it's involving the vector X, it's very similar to what we had before. And then instead of the observation vector Y, we've now got the basic actual over expecteds R0J. So for each LSOA, we carry out that optimization, and then we set the relative risk F1 of I to be that point estimate. And that's the relative risk, which is accounting for socioeconomic factors. And then lastly, we're going to update the expected death. So that's the basic expected deaths, and then multiplied by the relative risk to give us D1 hat. So how do we calculate the weights? Well, first of all, some weights are set to 0, and in particular, for the LSOA itself, we set that to 0 so that we have immediately have a sort of out of sample data set. And we also attach weight 0 to any LSOAs which have a different urban-rural classification. Otherwise, the weights depend upon the distance, but it's the distance in terms of distance between the predictive variables. So it's not physical distance in terms of geography, it's in terms of the socioeconomic characteristics. Are they similar or are they far apart? And so the more different the socioeconomic characteristics are, the more the weights go down to 0. So moving now into stage 2, so we've got the updated expected deaths, and then we calculate the updated actual over expected. Now what we're going to do is to add in location data. So here y is the location coordinates, latitude and longitude, and we're going to smooth the actual over expected that we had up here. We're going to smooth that using the location data. So there's a rather simpler formula for the location-specific relative risk. We then look at the fitted expected death rates, and so it's now the baseline multiplied by the F1 and F2 to give us expected deaths D2. And as I mentioned before, the weights here depend upon the physical distance between two LSOAs. Now to move on to the data and the results so far. So we're going to look at the period 2001 to 2015. We'll also look at 5 different 10-year age groups, 40 to 49 up to 80 to 89, and we'll just talk about how the model fits and the relative risks, how they vary with age group. And the predictive variables that we're going to use in this analysis are income deprivation and employment deprivation, but income deprivation is going to be for the elderly only, rather than the whole of the population. And then employment is obviously going to be linked to the younger ages. We're also using average number of bedrooms, living environment deprivation, and wider barriers. We also use the percentage that are in a care home above age 60, with nursing and without nursing. They're very important, and also the urban-rural classification. Now, this chart here is looking at the actual over expected, but it's without having done modeled any socioeconomic effects. So what you can really see here is that it really is a complete mess. You can maybe just about see some hot spots in terms of more reds in certain areas, London and some of the bigger cities in the north of England. We can do a bit of smoothing, spatial smoothing, so I'm still not here modelling any socioeconomic effects. I'm just smoothing out a bit of the geography that we've seen in the previous slide. And what you now can start to see emerging are that the hot spots are really in the big cities, and then outside of the big cities that mortality is tends to be a bit lower than the national mortality. And then focusing in on London, we can see that most of central London has relatively high mortality, with the exception of this sort of blue and green area, which is Chelsea and Kensington. And then the other blue areas are the more affluent suburbs around the outside of the outskirts of London. So now let's go back to the socioeconomic specific relative risk. So these formulas are just reminding us what went on in the earlier slides. And as a starting point, we might ask, how dependent is F1 on the urban-rural classification? So does it make a difference? So in this chart, I'm doing a scatter plot. Each dot represents one LSOA, and we fitted the model twice. So in the first time round, we ignore the urban-rural classification, and then the second time round, we include the urban-rural classification. Now, if the classification didn't matter, then all of these dots would lie on the straight line x equals y. But for example, if we look at the blue dots, we can see there's a bit of curvature. It's not as steep as the x equals y line. And this curvature here tells us that at least if you live in an urban-rural if you live in a rural area, then the mortality rates are not as sensitive to the underlying socioeconomic factors. Now, summarising the role of the predictive variables, so the ones that matter most are up here, so the employment deprivation and income deprivation. Employment is the key driver for the younger age groups. Income deprivation for the elderly is the main driver for the older age groups. Urban-rural classification, that's also an important driver. And then we had the other socio-economic variables, such as bedrooms, living environment, wider barriers. These are second order, but they are nevertheless significant statistically. And then lastly, the care homes. Well, these are very much nuisance variables because they're not really telling us about the socioeconomic effects within an area. But we do need to take account of these when we're looking at observed mortality, because clearly if there's one or two care homes in your particular area, then we would observe more deaths simply because of these care homes being in that area. So it is important to include these, and the good thing is that the methodology allows us to filter out the impact of care homes on individual mortality. So for example, if you look at the results, then the males in the highest age group, 80 to 89, so if they were in a care home with nursing compared with not, then mortality is 3 to 6 times higher. Now let's look at the location-specific relative risk, so F2. So we had this question earlier on, when we see the geographical variation, how much of that is really down to socioeconomic factors and how much of it genuinely is some other geographical effects that we find difficult to model. So this is a map of the location-specific relative risk. It's looking at males in the 40 to 49 age group. Now, what we can see here is that there's very much not a sort of north-south divide in terms of high or low mortality. We see a rather complex pattern, so that there are some hotspots in the north, but equally we can see this sort of red and orange ring, which is out to the south and west of London. So we might speculate as to what that is, but it's perhaps not what we were expecting in terms of a north-south divide, in terms of what we observe in mortality rates. Then if we move now to the males 60 to 69, the sort of hotspots to the west of London are now a bit closer in. Previously they were a bit further out. Again, some sort of sporadic hotspots in the north of England. And then the other thing that we see in this chart is an emergence in the southwest of England of some blues and greens. And for this particular age group, we might associate this with healthier people who've got a good pension taking early retirement and retiring to the southwest coast of England. And then lastly, for 80 to 89, a different picture again. And so the hotspots are now moving up towards the north, but again, it's they're not so sort of widespread in the north compared to the south. We can then zoom in on London, so just remember with London, the whole of the centre of London had relatively high mortality, but that was really because of socioeconomic factors. When we now look at the spatial effects, we can see that there are generally high mortality in the west of London and generally low mortality in this smaller area in the north, and again still in the sort of Kensington, Chelsea sort of area. So that's for 40 to 49, and then for 80 to 89, still some variation across the city, but the hotter spots have now moved over towards the east of the city. Now, these two charts are comparing the socioeconomic effects and the spatial effects. So on the left, we see the socioeconomic effects, and on the x-axis, we've got the relative risk for the socioeconomic effects, so F1. And this is an empirical cumulative distribution function. So if we're looking at the, say, at the 40 to 49 age group, the black line, what I take from this is that as much as, or nearly 10% of the population within this age group, 10% have mortality rates which are less than 50% of national mortality. So that's going to be the well-off groups in society. But then at the other end, there's also maybe about 7 or 8% at this level that have mortality rates that are more than double the national mortality. So a very big difference between the well-off and the much less well-off. What we also see in this chart is that there's a gradual steepening of these curves, so that in terms of inequality, in terms of mortality, there's much less of a difference between the most deprived up here and the least deprived. So it's a gradually narrowing gap, which is something that we see in other data sets. On the right-hand side, on the same scale, it's the location-specific relative risk. And the key takeaway here is that these plots are very much steeper than the socioeconomic relative risks on the left-hand side. So this is really telling us that we've modeled the socioeconomic effects, and these have really captured most of the variation that we see across the country, and there's very little genuine location-specific risk. And indeed, if we look at the variances, location contributes only, depending on age group, it only contributes 1.3% up to 3.5% of the variance in the relative risk. Now, we can turn that into effective ages. So it's the same plots, but I've just changed the x-axis. So for the 40 to 49 age group, this bottom 8% that we have here, these are people who are as if they were 6 years younger than the national mortality. So they're in terms of lower mortality. And then at the right-hand side, for the most deprived in society, their mortality rates are as if they were 6 years or more older. So if we come back now to this table that we showed earlier on, so we started off with not modelling any effect, and we saw that the northeast had high mortality, the southwest had low. With our modelling, we incorporate the socioeconomic effect first, and we can see now that the gap between the different regions has narrowed very considerably, so that the highest mortality is now in the northwest, 102%, whereas the lowest mortality is still in the southwest, but it's not quite as extreme as it was. And then with the full model, it's still not exactly 100%, because we're not, the way the model is fitted, it's not targeting 100% in each of the regions, but again we see that finally closes the gap even more. And we have similar patterns for other age groups and for females. Now, all of those charts were for 2001 to 2015, and that would allow us to do 1 year out of sample. We can also look at two non-overlapping 8-year periods and compare the results for these. So this is just an example for the location-specific relative risk, ages 70 to 79. So although we can see that there are some differences between the two charts for the different time periods, that we can still nevertheless see that the hot spots and the cold spots, the blues, do tend still to be in the same sorts of areas. We can look at scatter plots. So again, each dot is for individual LSOAs. So we can look at the two 8-year periods, 2001 to 8 versus 9 to 16. Different colours represent different urban-rural groups. Now for this chart, for the socioeconomic risk, there's a sort of thin grey line, which is the x equals y line, and we can see that the scatter plot is just a bit steeper than the x equals y. And what we interpret from that is that the inequalities between the most deprived and the least deprived, those inequalities have got a little bit wider between the two periods. So that's the socioeconomic risk. And on the right-hand side, we've got the location-specific relative risk, which is on a different scale. It's much more spread out. And the reason it's more spread out is largely due to the effect of sampling variation in the data set. So the numbers of deaths, even though we're adding up over years and ages, that the numbers of deaths are still quite small, and that leads to some variation in some sampling variation in the point estimates. So again, it's sort of reasonably well aligned. It's maybe slightly flatter than the x equals y line, but that's difficult to say for sure. So there's no strong evidence for a change in terms of the spatial effect. We can also look at different age groups. So this is the two plots looking at the socioeconomic change between the two periods for 40 to 49 on the left and 80 to 89 on the right. So for 40 to 49, the scatter plot is mainly aligned along the x equals y axis, so not much change between the two time periods. The one thing we do see, however, is that the orange dots, and the orange dots are London, and that is telling us that between the two 8-year periods, that the gap between the most deprived and the least deprived, that gap has narrowed over from the early period to the later period. And so that's something that needs to be investigated further in terms of what the reasons for that are. In the right-hand plot, it's the higher age group, 80 to 89. All of the urban-rural groups are quite similar, and we can see here that it's got steeper, so similar to 70-79, and that steeper is telling us that the inequalities have become bigger between the two 8-year periods. So just to round things off, so what we've seen here is that the spatial and regional effects are statistically significant. However, they are, as we've seen in the plots and the charts, that these are very much less important than the socioeconomic, the non-regional effects. And then we have to think about what are the next steps. So both effects, can these be used so that's the socioeconomic and also the location-specific effects. So can these be used to improve predictions of insurance and pensions mortality? So it might be that we take away our set of predictors, but not necessarily use these as given in terms of the relative levels of mortality, but to use these as an additional predictive variable that people might use in their life insurance or pensions data set, and they might be used alongside other information such as pension amounts or postcode data to see whether with this extra predictive variable from our analysis, whether that can improve your predictions of mortality. An alternative line is to think about forming other clusters of LSOAs. So early in the presentation, I talked about the IMD deciles, but perhaps we can construct data sets which are perhaps representative of life insurance data sets, for example, but which have particular characteristics which are based on the data sets that we've been looking at here and our results. So that rounds off the presentation. So I finally want to just thank you for watching this webinar. And if you want to find out more about the research, then you can go to one of our websites. So there's the ARC, its own main website, www.actuaries.org.uk/ARC, or there is the project website where we have rather more in the way of our most recent conference presentations, as well as the papers that we've got published. And we'd very much like to hear from you, so you can email me at this address, a.j.g.cairns@hw.ac.uk. So thank you.